a great honor to be here to talk about the mirror symmetry for parabolic Higgs bundles from local to global. And here is the outline of my talk. And since the audience may not familiar with this topic, and firstly, I will briefly introduce the history of Higgs bundles and parabolic Higgs bundles and the motivation of this project. And then the topic will be divided into two parts. The first part is about local mirror symmetry, and it's correspond to the name local. And this part is based on the joint work with Baohua Fu, Yongbin Ruan. And in this part, I will introduce the nilpotent orbits and tell you the seesaw phenomenon we found, and we call the range of the seesaw phenomenon the footprint, and then you will see that this kind of phenomenon is quite important in both local mirror symmetry and global mirror symmetry. And then I will show you the mirror symmetry for parabolic covers of Richardson orbits. And the second part is about the global mirror symmetry, and this part is based on the in-progress work with Wei Changhe, Xiao Yushu, Bing Wang, and Yaoxiong Wen. And actually, this is not me, and this is my one of my collaborators. They happen to be the same character here, but the Chinese character are different. And in this part, I will tell you the SYZ mirror symmetry and topological mirror symmetry for parabolic Higgs bundle. And okay, let me start. It is known that in 1986, Hitchin studied the space of special solution of self-dual equations, which is come from the 4D super Yang-Mills theorem in physics. After the dimensional reduction, which will gives you the following Hitchin equations, and to study the solution of the Hitchin equations, and it turns out that the solution space is the modular space of stable Higgs bundles. It's denoted by the follow. This modular space is parameterizing tuples. Here C is a fixed smooth algebraic curve of genus G. In usual, people will assume the genus is greater than 2. And this bundle E is a vector bundle of rank R over C. And the phi here is called the Higgs field, which is a map from E to E tensor, the canonical bundle of C. Since this bundle is SLR bundle, so the determinant of this bundle is trivial. And so usually people will twist it a line bundle in the beginning with degree D line bundle twisting in the beginning. So this D corresponding to the fixed line bundle. Okay, so this modular space has rich structures. First of all, it admits a hyperkähler structure. And furthermore, there is a well-known Hitchin map denoted as follows. For points inside the modular space, E and phi, and the Hitchin map maps the pair to the characteristic polynomial of the Higgs field. And this Hitchin map actually is projective, and this curly A is called the Hitchin base, which is a affine space defined as follows. Actually, this is a coefficient of this characteristic polynomial. And this Hitchin map makes the modular space into a completely integrable system. And many years later, Hassel Cedars studied the G-Higgs bundles over C for the group G equals SLR and PGLR. These two groups are Langlands dual groups. And actually, this PGLR is the SLR quotient by ZR. And due to this finite quotient, and this PGLR Higgs bundles can be realized as a finite quotient of the SOR Higgs bundles by the finite group gamma. This gamma, the capital gamma, is the R torsion of the pK 0 of C, and the action of the gamma is defined as follows. It's just tensoring by this line bundle, and this is this moduli space is actually a orbifold, and in the same paper they propose two kinds of mirror symmetries. One is called SYZ Mirror Symmetry, and another one is called Topological Mirror Symmetry. I will tell you the definition of them in minutes. And for SYZ Mirror Symmetry, first one should notice that given a Langlands dual group, the Higgs moduli space will map to the same Hitchin base. We denote by curly A here, and this H and LH denoted by the Hitchin map on both sides. And the SYZ Mirror Symmetry state as follows: for a generic points of the Hitchin base, say the A, and we consider the inverse image of the Hitchin map on both sides, and the SYZ Mirror Symmetry says those two generic Hitchin fiber are spatial Lagrangian and dual abelian varieties. And for the spatial Lagrangian, one should notice that for the Hitchin map, it is known that this Hitchin base is of half dimension of the moduli space, and so the Lagrangian structure is easy to see, and the spatial Lagrangian is coming from the hyperkähler structure, and the dual abelian variety, the abelian variety structure is coming from the so-called BNR correspondence. Roughly speaking, this correspondence says that the points of the tuples vector model E and the Higgs field phi can be realized as a line bundle over the spectral curve over C. The spectral curve is defined by the characteristic polynomial inside the total space of the canonical bundle of C, and this is called the spectral construction. And the dual abelian, the dual abelian variety, the dual condition is coming from the finite quotient of the two moduli spaces. And this is SYZ Mirror Symmetry for type A. And to introduce the topological mirror symmetry, I have to say something about the strange E functional. Let M be a normal variety with only canonical singularities, and consider a log resolution as follows. That means the exceptional locus of the row here is a divisor whose irreducible components, say D. D1 to the following form, with the coefficient of the irreducible components is greater or equal than 0. And then for n subsets of I, 1 to S, and we define the following set, dj, which is the intersection of d small j for indices j inside the capital J, and denoted by the dj circle, the smooth part, smooth locus, and then the strange E functional of M is defined as follows. It's first you consider all the possibility of the subsets J, and then you consider the this is Ewell's E polynomial, or the Hodge-Delling polynomial, defined by using the mixed Hodge structure of the dj circle. And this part is you can think as some kind of degree shift. by using the the information from the irreducible component of a divisor, and then finally you obtain the very complicated formula for the strange E function. And it is well known that this strange E function is independent of the choice of resolution. So to compute the strange E function, first thing you should do is to find a good log resolution, and then and all the data you need to compute it. We will come back to the computation of strange E function later. And let me tell you the statement of topological mirror symmetry, which is the equality of the strange E functional of two moduli spaces. And in the same paper, Hassel-Seder successfully proved for the rank equals 2 and 3. The reason is that their proof is to use the Seesaw localization technique. The Seesaw action is acting on the Higgs field, so the fixed locus becomes into two parts. One is called the monopole branch, and another one is called the instanton branch. And the instanton branch is stable bundles over the curve. And when the rank become larger and larger, the monopole branch become more complicated. So that's the reason why they only successful in proving lower rank. And for general, if R and D are co-prime, that means the semi-stable locus equals stable locus. So that means the SOR Higgs bundle model space is smooth. Under this condition, there are two proofs of the topological mirror symmetry in general. One is by Grothendieck and Reis and Ziegler. They use the p-adic integration technique. And another proof is given by Malik and Shen, and they use the shift theoretical way to prove it. These two proofs are very different. Okay, so that's a story for the Higgs bundles. And for the parabolic Higgs bundles, which will be back to 2006, Kapstein-Witten initiates a program to study a Langlands program through 4D gauge theory and S duality. And in the same year and 2 years later, Gukov and Witten introduced the surface operator in gauge theory. Roughly speaking, in mathematical way, it says that after dimensional reconstruction, we not only consider the Hitching equations, we also need to consider Hitching equations with singularities. This singularities here means the Higgs field we consider may have poles at certain points. And then if you look at the spatial solution of this equation, and after the change of variables, and you obtain these equations. This equation is very known because it has a name that it is called the Nernst equation. And then by consider the spatial solution of this Nernst equation, and you will obtain the co-adjoint orbits. This equation was first used by Koheimer to construct the hyperkähler structure for the co-adjoint orbits of certain type, and it was generalized to any type by Kovalyv. Okay, here comes the ingredients we will use later, co-adjoint orbits, and in mathematical literature, the Hitching equations with singularities were first studied by Simpson. So for simplicity, in type A, and if we fix one point of the smooth curve C, And a filtration, also fix a filtration of the vector space. The vector bundle restrict to the points is denoted as follows. So this is a filtration of the vector space EX. And what's the data of the parabolic Higgs bundles? It's still the tuples here, but one should notice that first, the Higgs field may have the poles at the X, so we twist by the OX here. And then since the Higgs field may have the pole, and we require the residue of the Higgs field at the X preserves the filtration. What does the preserves mean? There are two types of preservation. One is called weakly preservation, and another one is called the strongly preservation. For the weakly preservation, that means the residue of the Higgs field at X maps EI into EI. And for the strongly preservation, it requires that this guy maps EI into EI plus 1. So in the language of Lie algebra, the weakly preservation means the residue of the Higgs field at the point X lies in the parabolic subalgebra associated to this filtration. And the strongly preservation means this guy lies in the new radical of the parabolic subalgebra associated to this filtration. So in the following, we will focus on the strongly preservation, and also that means this guy is nilpotent. Okay, in type A, my collaborators they proved the SYZ Mirror Symmetry and Topological Mirror Symmetry. And I leave a remark here. Since in type A, there is a one-to-one correspondence between classes of filtration and nilpotent orbits. And furthermore, the input data of nilpotent orbits for both moduli space, one is SUR parabolic Higgs bundle, and another one is PGR parabolic Higgs bundles. The input data are the same, but that is not true in general. So that will cause much more, that will cause scientific difficulties. And our goal is to understand and prove the SYZ and topological mirror symmetry for parabolic Higgs bundles of type B and C. So the first natural question is, what should be the mirror input data? And as I mentioned, that the parabolic Higgs bundle, roughly speaking, can be viewed as Higgs bundle plus the parabolic structure, and the parabolic structure somehow is related to the nilpotent orbits or the closure of the nilpotent orbits. So the question here may turn into the following question: what should be the mirror nilpotent orbits? And the first expectation is the mirror pair should share the same dimension. This expectation is coming from the SYZ mirror symmetry. As I said, because in the SYZ mirror symmetry, the Hitchin base should have the half dimension of the moduli space. So if the dual moduli space share the same Hitchin space, that means the dimension of dual moduli space are the same. And we know that the G-Higgs bundle and G-dual Higgs bundle have the same dimension. So by this rough idea, the first expectation should be the input data have the same dimension. And the second expectation is that the mirror pair should share the same strange E functional. This expectation comes from the topological mirror symmetry. Suppose that parabolic Higgs bundle is just a smooth vibration over the Higgs bundle, And by the factoriality of the strange E functional, we know that the fiber should share the same strange E functional. So this two is very natural, and then we will answer these two in the following. Okay, so what's a nilpotent orbit? Suppose G is a complex semi-simple Lie group of classical type, and the small g is its Lie algebra, and choose a nilpotent element denoted by x inside G, and we denote by the OX the joint orbits of the G action on X. Here G is a joint action X on the X. And it is known that nilpotent orbits are classified by a certain type of partitions. For example, in type AN, D is a partition of n plus 1. Suppose n equals 10. In SL11, we can have adding partition of 11. For example, like 6, 3, 2. And for a partition, we means that this guy is greater or equal than this guy, and so on. And in type B, the D is a partition of 2n plus 1, and the extra condition is that the even parts appear even times. We see even parts, we means a number inside the partition here. So take n equals 4, and in SO9, we can have partition like 4 or 5 to 2. Since 2 appear twice, satisfy this condition. So this partition gives you a nilpotent orbit inside SO9. However, if you consider 5 to 1, 1, which is not allowed since the even part 2 doesn't appear even times. Okay. Similarly, in type C, the D is a partition of 2n. The extra condition is that the odd part appear even times. For example, take n equals 4 again. We consider SP8. So the partition 332 is okay. But however, the partition 431 is not allowed, since in the 431, 3 is an odd part, but doesn't appear even times. Okay, this is a rule of partitions for nilpotent orbits in type B and type C. And also one thing one should notice that is given any adjoint orbits OX, the X may not be nilpotent. So if the orbit is close, if and only if X is semi-simple. So from this property, we know that nilpotent orbit is never close in the Lie algebra. And to introduce the closure, we have to say something about the partial order. We see a partition D is greater or equal than F if the summation of Di is greater than the summation of Fi for any k greater than 1. So by using this partial order, the closure of the orbits is just the union of the disjoint union of all the smaller or smaller orbits together with itself. This is a closure. And it is known that the closure is not smooth, and in general, it is even not normal, but it has symplectic singularities. And yeah, let me show you the picture here, which are all the nilpotent orbits in SO7 and SP6. Yeah, in the following, I will not distinguish the partition and orbits. And you can see here, there are almost 1-to-1 correspondence on both sides, except something happened here. Yeah, I will tell you what actually happened. So among all the nilpotent orbits, there are something special we call the special orbits. Actually, this special orbit, the name of special orbits is related to the representation theory. I won't go in detail here, but in terms of the partition, we see nilpotent orbit is special if the transpose partition is still of the same type. Yeah, let me use examples to see to tell you what does that mean. So suppose we consider the orbit 2211 in SP6, and we draw the Young tableau of 2211 here, 2211, and take its transpose, and then we will get the partition 42. Since there is no odd part here, so this partition is of type C, is of the same type. Thus, this orbit is special. However, if you consider 2 and 1 to the power of 4, and you can compute the transpose easily, which is 5, 1, and it is not of type C, so 2 and 1 to the power of 4 is not special. Okay, yeah, let's back to this diagram again. Actually, by the way, this diagram is called Hasse diagram, and the partition in red is non-special. It's not special. So if you erase all these non-special orbits, and the remaining special orbits are actually one-to-one. There is a one-to-one correspondence to each other. This is not an accident. It is guaranteed by the Springer theorem. By the famous Springer theorem, there is a one-to-one correspondence of the special orbits in type B and type C, which we denote the map as S here. And we denote the Springer dual orbits, the SO, like this. And this map is also known as order preserving and dimension preserving. Yeah, let's take a look at the part of the Hasse diagram I showed you before. So these two, this one is special. So and they are due to each other, Springer due to each other. And you can, by easy computation, you can say the orbit is of dimension 10, and here is also of dimension 10. However, this guy is non-special, and which is of dimension 8. And however, and on the right-hand side, this guy is of dimension 6, and there is no other orbit between dimension 10 and 0. So there is no correspondence between these two on both sides. Okay, yeah. Let's recall the first expectation. We say the mirror pair should share the same dimension. It seems that the special nilpotent orbits satisfy this expectation. So the following is to test whether special nilpotent orbits have the same strength E functional. Yeah, let me tell you the answer first. Because this naive thought fails. It just consider the baby example I showed you before, the two spatial orbits, 3 and 1 to the power of 4, and 2, 2, and 1, 1. Later, I will tell you how to compute the strange E functional, and we will say later they are actually not equal. So, yeah. Then here, this arises another question: how to remedy this failure? And yeah, to remedy this failure, we need to introduce another notion, another notation. Among the spatial orbits, there are something more special, which is called Richardson. We see our nilpotent orbits is Richardson if there exists a parabolic subgroup P such that the moment map mu P, the image of the moment map mu P from T star G mod P surject on onto the is onto the closure of the orbit O, and we call this parabolic subgroup a polarization of this Richardson orbits, and denoted by the POLO on the set of classes of all polarizations. And okay, what makes the Richardson orbit so special? The first is that if this usually in general the Springer map, this moment map is also called Springer map. The Springer map is generically finite. If the degree of map is equals 1, then this becomes a resolution. Actually, it's a equivalent resolution. Then it is a sympathetic resolution. Conversely, given any nilpotent orbit closure, if it admits a equivalent resolution, say have a map rho Z to the O bar, and then the O is Richardson, and this resolution Z is isomorphic to T star G mod P for some parabolic subgroup. This is so special. Okay, yeah, let's back to our baby counterexample. So actually, these two, yeah, sorry, I forget to say, is actually Richardson, and for the left hand side, there is a equivalent resolution of this orbit closure, and on the other hand side, if we consider the Langlands dual group and we consider the Springer map here, this map is of degree 2, and so since this one is equivalent resolution, and then equals the E polynomial of this smooth resolution. And then by Algebraic computation, you can obtain the following results. And I will tell you later how to compute the right-hand side. But let me tell you the answer first. The strange E functional of the right hand of this nilpotent orbit closure equals this. And then by easy compare of these two, you'd see that this guy does not equal this guy. However, by Algebraic computation, one finds that the E polynomial of T star G dual quotient P dual actually equals the E polynomial of T star G mod P, which equals the strange E functional of the this orbit closure. So what does this mean? This means follows. Since this guy is mirror pair to this guy, and however these two this one is a equivalent resolution. So this tells you this one is somehow mirror to this orbit closure, and this picture gives us a hint to remedy our failure, in that maybe we should consider certain cover of the nilpotent orbit closure. What does that mean? Actually, I will tell you in a minute. So in general, if you consider the parabolic subgroup inside G and the dual Langlands dual group inside G dual, and you will have the following results. The first row is Langlands dual, and you consider the Springer map, and those two will map onto two orbit closure. However, it can be proven that these two orbits are Springer dual to each other. So that means the first row is Langlands dual and the second row is Springer dual. They are somehow magically fit into this picture. And moreover, we found the following Seesaw property of the degree of this two Springer map. The degree of the product of degree of these two map equals the order of this group. This group is called lucid canonical quotient group, which is very important in representation theory. And actually, this is serious. And you will see later, this equality is very essential, both in local Mirror symmetry and global Mirror symmetry. Okay, taking the stem factorization of our picture, and we obtain the xp and x dual p, and by taking this stem factorization, we know the pi p and pi dual p are birational, and nu p and nu dual p are finite. And we call this xp and xlp the parabolic cover of the normalization of nilpotent orbit closure of these two. Since the T star G mod P has trivial canonical bundle, so it turns out that this birational map is actually a equivalent resolution. So the strange E functional of this guy equals the E polynomial of this guy. And by easy computation, you can find that the E polynomial of this guy equals the E polynomial of this guy. So that means the strange E functional of this parabolic cover equals the strange E functional of the dual parabolic cover. And this is our result of the local topological Mirror symmetry. It is the dual parabolic covers XP, the same G functional. And furthermore, we collect the set of the degree of the Springer map, and it will form in this way. I won't go to detail, but we call the set of the pair of degrees the footprint. Actually, this footprint is quite important. Why? Let me tell you in this. So let's take these two again. Group equals Z2, and then all the polarizations. Those two have only one polarization under the conjugation. I denote by P and L, P dual, and the degree of the Springer map for this P is 1. I just mentioned before. So we have the T star G mod P to the orbit closure here, which is a equivalent resolution, and on the right hand side, this guy is of degree 2. So the footprint in this case is 1, 2, which is not symmetric. Usually, people prefer something looks symmetric in the Mirror symmetry. But however, this footprint is not symmetric, which means there is no 2, 1 here. So if we consider the 2, 1, which means this degree is outside of the range of the footprint. So what will happen? Actually, we can construct such kind of stuff since the pi 1 of the closure is mirror to actually the stem factorization of this here. the parabolic cover of this guy is mirror to this guy. And if we consider the double cover M here, whether this M is mirror pair to this guy. So yeah, unfortunately, it is still not true. In following, for simplicity, I denote this orbit OB since this is of type B and this guy OC. In following, I will show you how to compute the strain E functional somehow in general, and you can see why these two are not a mirror pair. Okay, so first question is that what is M? Here we have the answer. The M is somehow is a orbit inside type D that is in SO8. We have the SO equivalent double cover.
Have you changed slides? Because I think your slides got stuck.
Oh really?
Okay, now I got unstuck. Okay, sorry.
Okay.
I got lost at what is M. Okay, yeah, good. Thank you.
Oh, thank you. Yeah, maybe my internet is not so good just now. Okay. Okay, here we have the answer for the M, which is a orbit closure inside SO8. Well, I just for simplicity, I take the special case in our proposition. We can do more complicated cases. Somehow in general. To compute the strain E functional, we need to construct a log resolution. There is a so-called Jacobson Mirror resolution for nilpotent orbits. For any a nilpotent orbit, not necessarily special. I won't go in detail, but it looks like this one, some kind of G cos a P module, and you quotient by P for on both sides. So this is a resolution. Okay, so in above example, we can see the NC and ND can be viewed very simple as the symmetry power or the white power of the certain vector space. And our strategy to the Jacobson Mirror resolution is usually not a log resolution. So we have to construct a log resolution from it by successful blow-ups. Here is the strategy. We consider the denote by MK the element of rank K inside the NC or ND, and we blow up along this MK successfully, and finally we will obtain this ZC hat to our orbit closure. and it can be let's recall a bit. In our to compute the strain E functional, we need to know what is the DJ circle, and we also need to know the coefficients inside of the irreducible component of the formula of the canonical bundle. And actually that is doable. Here is the answer. It looks a little bit complicated, but somehow it is doable. And if in the end, what we will get is in this example is that, so for a little bit, this OD bar is a double cover of this OB bar. So and then we want to compare the strain E functional of this OD bar and OC bar. And here is the answer. Actually, in our paper, we can do more. Here, we just, for simplicity, we focus on this. maybe examples. And here is the answer. So you can see they are not equal. And this calculation is the importance of the footprint in the mirror symmetry. Okay. Let me firstly, we need to construct a model space associated to this orbit closure. And I said, usually the model space you want it become smooth, so you cannot insert the something not smooth for your input data. And what we input is something here. There is another interpretation of this GPN2. Tells you how your Higgs field preserve this spatial flag in certain way. And so by using this input data, we get the new model space, namely denoted by JMH. Here I use O bar to emphasize this model space is related to the orbit here. Okay, so this model space is also parameterizing tuples, and you can have the Hitchin map and also Hitchin base. And however, here the Hitchin base should be modified a little bit by this form. I will use an example to tell you what's the delta partition. But here the delta I is called the set of delta I is called the singularity of the spectral curve. As I mentioned that in Higgs bundle, in Higgs bundle the spectral curve is actually smooth. But however, in the parabolic Higgs bundles, due to the nilpotent orbit data, the spectral curve usually is not smooth. So this delta I is somehow characterize the singularities of the spectral curve. However, this one is not. This map is not surjective in general, but one can prove that if the orbit O is special, and then this Hitchin map is. Let me use a quick example to tell you how to define the delta I. Let's consider the orbit 5542 in SP16. Excuse me. First, you draw the Young tableau as follows: 5542, and you label the first row by 1, the second row by 2, and so on. And then you pick up the every 2 number in the every 2 number here. So you pick up this one, this one, this one, and so on. So and then you obtain the delta 1 to delta 8, which is 1, 1, 2, 2, 2, 3, 3, 4, the star here. This is the data of the spectral curve corresponding to this orbit. And let me use another example, which is in SO17. Let's see, here is in SP16. Actually, this orbit is Springer-Due Richardson orbits of type of previous one. So you can see, similarly, you write 5, 5, 5, 2, 1, 1, and then you pick up every 2 number. And surprisingly, you finally obtain the same set of delta I. This is not an accident. However, we have the following theorem to characterize the spatial orbits in some sense. So given two nilpotent orbits, OB and OC, and we see that they are both spatial and correspond by the Springer dual. I mean, they are Springer dual to each other and spatial if and only if the following two condition holds. The first one is the dimension of the model space are the same, and second one is the singularity of the spatial curve are the same. So this kind of interpretation may gives you another meaning of the spatial orbits in another way. Okay, so now in the following, we focus on the spatial orbit input data. Oh, sorry, here I make a typo here. This orbit, here I want to say it is Springer dual of this orbit. Should be SOB bar denoted by OC bar. Just forget the S here. So from the above theorem, right now we have these two model space share the same Hitchin base, denoted by PA here, emphasize the parabolic structure. And then, but however, one can show that the generic Hitchin fibers on both sides are abelian varieties, but unfortunately they are not dual abelian varieties. To remedy this problem, in Richardson cases, we should consider following data. So the first, the lower row is the model space we introduced just now, and the upper row is model space introduced very beginning of my talk. It's associated to the recall that since here we consider Richardson orbits, these two orbits may have the Springer map, which is from T star G mod P and T star G dual mod P dual to its closure. So this model space is given by the data of parabolic structure. In the end, those four model spaces will map to the same Hitchin base here. And this two vertical map is not the map for the model space. Sorry for the bad notation, but I want to say these two maps are the maps between generic fibers of these four model spaces. And one can show that the maps are finite, and the degree of these two, the product degree of these two equals the order of Lustig canonical quotient. This formula is coming from the theorem I showed you before. And then by using this property, finally one can show that given this that should not to be B, this should be PA. There is another typo here. Choose a generic point B inside PA, and the generic Hitchin fiber H0B and H dual 0B, H dual inverse B are dual abelian varieties. And then also one can, by using deformation theory, one can show those two model spaces have the symplectic structure, and by using the non-abelian non-abelian Hodge theorem, one can show they admits hyperkähler structure. So in the end, we can show the SYZ Mirror Symmetry for type B and type C in this picture. And finally, by using the similar p-adic integration technique, we finally can show the two moduli spaces share the same strange E function. Okay, yeah, I just stop here.